Hi everyone. Now that we've figured out how to determine whether a molecule is polar or not, we need to start talking about the intermolecular forces that we see between molecules. We've talked about intra versus inter in previous videos, and just as a quick review to get us focused on what we're talking about. When we talk about inter, we're talking between or among things. So if we're talking about a bulk substance where we have lots of molecules, say a glass of water or some hydrogen chlorides or hydrochloric acid, we have weak intermolecular forces which are between two molecules, and then strong intramolecular forces which are the actual covalent bonds. Okay, and this is important because when we're explaining how substances interact, it's important for us to be able to differentiate between these two types of interactions. With intermolecular forces, they are weaker than the intramolecular. Okay, these are the ones that sort of keep things together in a substance but don't define what the substance is. Okay, the things that define what the substance is are the chemical bonds within the individual molecule. Here we can see that we have a polar covalent bond. Okay, and our polar covalent bond is, of course, our intramolecular. And then we have forces of attraction between these that would determine whether or not HCl is a gas or a liquid or a solid at room temperature. Okay, so the properties of the substance result from the properties of the individual molecules, the intra in terms of how they chemically react, and then also how the molecules act together. Okay, so a lot of our physical properties will come from the interactions between individual molecules in a substance. The strength of the intermolecular forces determines the melting and boiling points. The strength of the intermolecular forces is determined by the strength of the attraction between the molecules, okay? Remembering that electrostatic attraction is between positive and negative charges. So if we've got something that is polar and has that partially positive and partially negative, we're setting up a situation where we could see stronger intermolecular bonds. That strength of the electrostatic interaction is completely dependent on whether the molecules are polar, non-polar, and how big or small they are. Examples of where we see intermolecular bonding making a huge difference to the substance is water. We know from our discussions on polarity that water is a polar molecule. Okay, we have a dipole here and a dipole here with an overall dipole because we have a non-symmetrical system. Okay, so the non-bonding pairs push down on the bonding pairs, giving it a bent arrangement. This bent arrangement means that the dipoles don't cancel out like we see in carbon dioxide, so we have a polar molecule. When water molecules are together in a substance, these dipoles align to form these intermolecular forces, which in water are known as hydrogen bonds, and we'll talk about those a little bit more later about how strong they are. But these intermolecular forces are aligned by the partial negative and partial positive charges on individual water molecules. So a key thing for this is where we talk about changes of state. So if we're changing from solid ice to liquid water, it is the intramolecular bonds that stay unaltered. We never break the chemical bonds that form water molecules. The water molecules always stay whole. You'll see here, this is a water molecule, this is a water molecule. We're never breaking the hydrogen-oxygen covalent bonds. This is not broken. What we are breaking is the intermolecular forces between water molecules so that they can spread out, so form a solid, then more so with a liquid and are able to move freely. And then finally, when we're a gas, where there's virtually no interactions between the particles at all. So when we consider these, we need to remember there's intramolecular bonds, which are always the covalent bonds, and the inter, which are the bonds that occur between molecules. We're not talking ionic compounds, we're not talking metals, it's only for covalent molecules. There are three main types of intermolecular bonds that we will talk about, and you need to be able to arrange in terms of their strength and discuss how they form. So we'll get started though on talking about not just the permanent dipoles that we talked about with polar molecules, but the other types of attractions that we can see. So we already mentioned that the forces are weaker than covalent metallic or ionic bonds. They determine if a molecule is a compound, is solid, liquid, or gas. If the intermolecular force is strong, then the boiling and melting points of the molecular compound is high. Okay, so it takes more energy to overcome those intermolecular bonds to change states, so we see higher boiling points and melting points. As I said, there are three types of intermolecular forces that can occur between covalent molecules. These are dispersion forces, also known as London forces. London forces can also incorporate all intermolecular forces, so I would steer away from that term, particularly in the VCE, as we want to talk about dispersion forces being our weakest type of force. Then we have dipole-dipole interactions, which occur between polar molecules, and hydrogen bonds, which are our strongest. With non-polar molecules, this is the first one that we're going to talk about, because with non-polar molecules, they have the same intermolecular forces that are present in all molecules. Okay, we know that with polar molecules, they have permanent dipoles, but in non-polar molecules, there is no dipole. So we're talking about molecules such as Cl2, where there's no difference between each end of the bond, or even something like carbon tetrachloride, where the dipoles cancel out. So there are dipoles present. We do have polar bonds, but they're arranged symmetrically around the molecule so that the molecule is non-polar. Okay, also noble gases, things like this, where there's no dipoles present. So some of these molecules are liquids and some are solids at room temperature, which means that they have something that can alter the way that they are attracted to each other. So we know there's some electrostatic force between nonpolar molecules in order for them to form these different states. So there needs to be something that causes a small attraction, or essentially there would be nothing. They would all be gases at room temperature. Nonpolar molecules will have what we refer to as an instantaneous or temporary dipole moment. If we consider the electrons that are in or around an atom in the electron cloud, those electrons are moving randomly. So this means at any particular point in time, the electrons can move more to one side than the other, which is what we see here. This would mean that in their bouncing in and bouncing out, the electrons are more on one side of the nucleus than the other. This polarizes our nucleus, okay, but so we can see a dipole. What happens is if we get a dipole, instantaneous dipole occurring in one atom, this can induce a dipole in a nearby one, which becomes polarized, and we see these weak attractions between molecules and atoms. So with these temporary dipoles, if we consider the bonding electrons within hydrogen, it's possible that these electrons will become symmetrically oriented, so it would be nonpolar, or for an instant they can jump to one side. This again is what we refer to as a temporary dipole, this time within the molecule. So if we consider that the average distribution of electrons would be equal, what we're talking about when we form a temporary dipole is that the distribution of the electron cloud becomes uneven just for an instant, and then this slight polarization will induce a dipole in a nearby one, and we will see an attractive force. All molecules, whether they're polar or non-polar, will experience instantaneous temporary dipoles, which means that they will experience induced dipoles, which are when they get close to something that has an instantaneous dipole. Essentially, this can spread throughout a molecule, and as you can expect, the size of the molecule and the number of electrons that can be manipulated in this way, where we get an instantaneous dipole, which will then cause an induced dipole, will influence the size of the dipole that is formed. So with an induced dipole, the electrons move to a different orientation and a new set of interacting dipoles will be created. It passes along the chain of the molecule. Over time, the orientation of the electrons in a specific space average out to produce no permanent dipole, but for instants of time within the molecules, we do see these dipoles coming up and going away. Okay, so they're very fast interactions, but they're also very, very weak because they're not there permanently. These weak forces are known collectively as dispersion forces and set the basis for the first intermolecular forces that we will look at and then go on and build from there. Okay, I'm going to leave this one here in terms of how we define intermolecular forces, and next video we will talk about dispersion forces, dipole-dipole interactions, and hydrogen bonding.